What's up, guys? So today we're going to be solving 938 range sum BST. The whole problem is basically when given a low and a high range, we have to go ahead and add up all the nodes in our current tree that are between that range. So in this example, given a low of 7 and a high of 15, we would need an answer of 32 because we have to add 10, 7, and 15. So let's think about this problem a bit further. Unfortunately, this is my third time recording it, so let's hope this time it works. All right, so let's think about this intuitively. We have our range 7 and 15. How do we go ahead and implement this in code? Well, there's many solutions. Basically, we just have to travel through every single node and check if our node that we're visiting is between this range. So the way I would do it is use a BFS. You could use a DFS, but I like BFS because it's very intuitive. We're just going to go level by level, checking every single node if it's between that range. Now, we need to also take advantage of the fact that this is a binary search tree. Now, the cool fact about a binary search tree is the fact that at any given node, for example here, we know that the left one is going to be smaller and the right one is going to be higher. And it's the case for every single node in this tree. I'm going to go through the queue implementation. I think it could help you if you don't understand BFS that well. If you already know, then you could go ahead and skip a bit. But for those who might find it helpful, stick around. First of all, we have to add our root node into the queue. And at every single pass, we're going to pop our current value. So we only have one value, so we pop 10 out, which means we have to erase it. But we have three things that we have to check every single time we pop a value. Is it in between this range? If it is, we add it to our global sum variable. And it is, so we do add it. Next, we know that in BFS, we have to check the left node first. Every time we have to add the left node first. So we got to ask ourselves, well, is it even worth it to go ahead and check the left node to check a smaller value? And the answer will depend on whether the current node is already smaller than the low value. Since it isn't, then we can say, well, yeah, it is worth it. So let's add 5 into our queue. We ask the same question, but in reverse for the right side. Is our current node already higher than our high boundary? If it isn't, then we add it, and it isn't. So we go ahead and we add it into our queue. All right, we finished one iteration. So now we pop our 5. When popping our 5, we have to go ahead and ask ourselves, is it between this range? It isn't, so we don't add it to the sum variable, but we still have to go ahead and check, is it worth it to check the lower value? And it's not, because 5 is already lower than the low value. So we don't add the 3, but it is smaller than our high value, so it's worth it to check a higher value. So we add 7 into our queue. The next thing we have to ask ourselves, now we finished another iteration, we pop our 15 and we ask ourselves, is it in between our range? And since our range is inclusive, yes it is. So we go ahead and we add this value into our sum. Then we ask ourselves, do we check the left value? No, there's nothing. Do we check our right value? Well, no, it's already at the extreme of our boundary. There's no point in checking a higher value because it's going to be above our boundary. So we don't add 18 into our queue. We finished another iteration, so we check 7, and 7 is in between our range because it's inclusive, but it's a leaf node, so our queue is completely empty now, and that's how we end our loop. Next, we just return our sum, which is 32, and that's about it. So let's look at the code implementation. So first of all, I've already initialized all that we need in terms of variables. So I've initialized our range sum, I've done the queue, and I've appended the root node and started our while loop. So first things first is we have to go ahead and check if our current node that we're going to pop right now, so node equals queue dot pop left, and that's it. So is that current node that we just popped, is it smaller than high? Is it bigger than low? And smaller than high? So if that's the case, then we go ahead and we add it to our range sum. Next, we got to go ahead and check the left value. Again, because we're using BFS and we know we always check the left value. So first of all, we have to check if the node.left even exists. And if it does, we take advantage of our binary search tree and we do node.val. Is it worth it to check the left value? Is it higher than our low variable? If it is, we do q.append node.left. Our right value is the exact opposite logic, so we just replace this stuff. We do if it's smaller than high, and here it's going to be right. All right, so let's test this out to see if I did any mistakes. There is an indentation mistake, so let's see if that worked. There we go. And you can expect some pretty good results with this, so let's look at the results. There we go. So the results are pretty good. You can expect about 70% beat on time complexity and very good space complexity. If this helped you in any way, shape, or form, please give a like and subscribe for more content like this. And I hope this helped you.